All right, so it is 8:31. Let's go ahead and get started. Okay, thank you again, everyone, for attending this morning. My name is Kyle Lake. I'm an application engineer with Oasis Sales, focusing on PADS Professional and Xpedition in the board system division for PCB design. So today is a tech talk. We're going to be talking about the Constraint Manager in the Xpedition and PADS Professional flow and some workflow and best practices using the Constraint Manager. So the Constraint Manager, a lot of people do find it confusing the first time that they look at it because there's a lot of information in there. Hopefully we'll learn today how to navigate that system, create rule schemes, create net classes, clearance rules, and constraint classes, and how to import a Stackup and see how that's going to affect our different constraints that we're going to define. Just a little bit about Oasis Sales, if you're not too familiar. We are a Mentor Siemens Premier Partner, and we have been for over 16 years. We are a distributor based in the Midwest and Northwest of the United States. We've worked very closely with Mentor, now a Siemens group, that to continue to provide our customers with the most up-to-date and advanced technology that they can get. Just a little bit about our team. So you see the states that are all highlighted. That is Oasis Sales territory. So if you fall into one of those, I can be your technical contact, and I've got my contact information in just a bit. Also, if you are in the East Coast of the United States, hopefully you're familiar with your reseller there, and that is TriLogic. We do have quite a few webinars on our website. If you go to oasissales.com, we have a lot of archived webinars that we cover on a monthly basis on just different topics in PADS Standard, Standard Plus, Professional, Xpedition, and hyperlinks for more of your simulation-based needs. I just do want to throw this out there just to save the date, a nice little notification for my next tech talk or advanced tech that I'll be talking about, and that's going to be the FPGA I/O optimization in the Xpedition flow. Really powerful tool that allows you to do intelligent pin swapping in order to unravel that rat's nest and make it a little bit easier to route when you're doing FPGA design on a board. All of our archived webinars are again at our YouTube channel as well, and we have a lot of short videos on there for demos or how to just maybe take a look and see if there's any good information for you. Here's my contact information. If you want to jot that down or take a screenshot of that, feel free to shoot me an email or give me a call anytime to discuss anything further that we discuss here today or any other technical questions. And I'll be showing my contact information at the end of the presentation as well. Okay, so now let's hop into our actual webinar here. Again, we're going to be talking about, it's a tech talk on the Constraint Manager, workflow, and best practices. Just to give a little bit more of a background on the PCB solutions from Mentor Graphics, we have 4 different real major product groups that we talk about in the board system division. Xpedition is the enterprise level PCB design tool, very powerful routing environment, as well as very high-end enterprise collaboration and data management capabilities. PADS, been around for a long time. A lot of people are familiar with it. It's more of a desktop or project-based PCB design solution. Still a very powerful routing environment. You can do a lot of complex boards with this tool. It's just not as much enterprise wraparounds for collaboration or data management. Hyperlinks is our PCB analysis and verification. Hyperlinks is a pretty broad range of families. You can do signal integrity analysis to EMI checking, to DC drop and DDR analysis. So there's a lot of different opportunities to analyze your board and do some virtual prototyping with hyperlinks. And then on the actual manufacturing and assembly side of things, we have Valor. In the Valor NPI does a lot of manufacturing and assembly checks for your printed circuit board. I like to talk about this slide. This shows the general trend in how PCB design has been going over the last 2 decades. And the major thing I want to take away from this slide is how the average leads per square inch, that highlighted red line, is just continuing to increase. Board size is staying about the same, maybe even getting smaller, but we're just packing more components, more traces, everything running through the board. There's just more stuff that we're trying to pack into the same form factor, and that can lead to a lot of different issues. So that is why it's really important to be able to develop constraints to constrain your design to make sure it'll work on the first time. And there's a good balance between over-constraining your design and not enough constraints. So you want to be able to complete it and complete it well. Okay, so what is the Constraint Manager? If you're unfamiliar, or if you are familiar with it, we're just going to start at the basics here. So the Constraint Manager is a spreadsheet-based constraint entry environment in the integrated flow for Xpedition and PADS. Okay, so there's a small screenshot down below on the bottom right that kind of shows what it looks like for defining our different clearances on a layer-by-layer basis. Okay. So some of the key benefits is that it automates the communication of constraints between engineers and PCB designers. It allows you to open it up from either the Schematic tool or the layout tool. So it's the exact same environment. You can enter the constraints in the beginning of your design process, or enter some of those constraints that you know you'll need in the beginning of your design process, and then you can work with the PCB designer in the layout tool to go ahead and further develop those constraints to constrain your design. Another key benefit is that we can actually cross-probe from the Constraint Manager in this spreadsheet-based system, cross-probe for nets, components, anything that you can select in the Constraint Manager, you can cross-probe it back into the Schematic or the layout tool, and vice versa. So if you select a net line in the layout tool, you can cross-probe that directly into the Constraint Manager and see what kind of constraints you have on that net. And like I did say, another benefit that we have with this tool is it might seem daunting at first to kind of understand and get used to. But once you play around with it, listen to this webinar, hopefully will help out. And once you start working with it, it's fairly intuitive and easy to understand how it works. Okay, so this is just a little slide on the integration of the Constraint Manager. So showing that in between the layout tool and the Xpedition Designer, being the schematic capture tool, we have this Constraint Manager. So we can set many different types of constraints with the Constraint Manager, from net constraints such as topology, delay, or crosstalk and differential pair, to the actual board rules such as net classes, rule areas, clearances, parallelism. That's all handled within the Constraint Manager. So it's a one-stop shop for all of your design constraint needs. And it's in between these two tools and accessible from the schematic or the layout. This is a good slide that shows how, or what the real process is of creating design constraints. Okay, so the first real step that we want to do is go ahead and set up our mechanical constraints, create those net classes, set up the constraints for those net classes, and assign nets to those net classes. Okay. Then once we go ahead and do that, we're going to assign those clearances to all of those net classes on a layer-by-layer basis, and we'll definitely walk through that. After we're going through ahead and doing mechanical constraints, we want to go ahead and take a look at the high-speed constraints for our high-speed signals. So we'll create some constraint classes, again, assign nets to those, and set up the net constraints on a net-by-net basis or a constraint class basis. So once we're done with that, we can go ahead and actually do the place and route. And what's powerful about the Constraint Manager is you can actually compare the routed data with what you have in the Constraint Manager. We have the ability to pull back that routed data from the PCB tool and compare it to what we actually set up in the design constraints, just to make sure everything's looking good. And obviously in the layout tool as well, you get real-time feedback for your design constraints. This just allows us to see what's actually routed and what we had planned in the Constraint Manager. So the first step, like I was saying, is to set up those mechanical constraints. And I wanted to define what a net class is, because there's a lot of confusion between net class and constraint class, and there's a little bit of overlap in there, but they definitely need to be understood in order to be successful in the Constraint Manager. So a net class essentially is a group of nets that have the same physical constraints on a layer-by-layer basis. So this means we want them to all physically act the same to other objects in the design. So we can set via assignments, layer biasing, trace width, and differential spacing for our different net classes. Okay, so it's really easy to go ahead, and you'll see right down there in the screenshot that we have our analog net class that we go ahead and define the typical trace width for that on a layer-by-layer basis. And we can also assign a via to that net class, or multiple vias if we would like, to that net class. Okay, and I would like to point out that there is a chat box at the bottom of the GoToMeeting screen. If you have any questions during this, please feel free to ask a question, and I'll definitely get to that as necessary. So clearance rules, very easy to understand. Clearances on a layer-by-layer basis. So just clearances between trace to trace to pad, via to via, plane to plane. Those types of clearances are the types of clearances that we'll set up in the clearances section of the Constraint Manager. So the next thing that we want to do is go ahead and set up the high-speed constraints. Okay, so very similar to a net class is what we call a constraint class in the Constraint Manager tool. And that is, a constraint class is just a group of nets with similar electrical requirements. Okay, so these electrical requirements can be length, minimum and maximum length, maximum number of vias, for example. If you want to constrain the amount of vias on critical nets, that's probably a good idea. And then matched length groups and certain layer lengths. We can actually define a maximum layer length on a net-by-net basis. Okay. And then once we have those constraint classes defined, we'll go ahead and assign those nets to the constraint class. Here we can also assign differential pairs, and within this tool it's very simple to go ahead and automatically assign differential pairs based on naming convention. A lot of people name their differential pairs _n, for example, and _p for positive and negative nets on that differential pair. And we have the ability to go ahead and take a look at that, and following that naming convention, go ahead and define all of those differential pairs at once. So if you have 50 differential pairs that you need to define, we can do it in one go, and it's very simple to go ahead and do that. Okay. So once we've gone ahead and set up our constraints, we can go ahead and route the board, place all of the components, and then route the board. And while we're routing, we actually have the ability to go ahead and look at our actuals compared to what our design constraints actually were set up as. This can be very important just to make sure that there's no errors. Like you'll see in that screenshot, that was a 0, so we haven't met that requirement yet of 3,500 to 4,500 mils of that length requirement for those nets. And what we can do after we compare all of those actuals in the Constraint Manager, we can create a report of all the violations and ship that off over to the PCB designer just to understand why we're not meeting some of our design requirements. And like I said, this is all a spreadsheet-based system. You have useful commands such as find. We can find anything within the Constraint Manager. Filtering, just very similar to Excel. We can filter on there. You can copy and paste. You can do the drag down just like in Excel to copy from multiple cells. And then we can add comments to cells for engineers to review. So if we add a comment in the Schematic tool, Constraint Manager, that will pass along, and the layout engineer can actually see that comment and understand why or where a certain constraint is. Okay, so now I'll go ahead and hop in the tool. I am going to just pull this slide up one more time. This is the constraint entry methodology that we're going to kind of follow. We're going to go ahead and set up some mechanical constraints, set up the high speed constraints, do just a little bit of routing, and then compare those actuals to see kind of how the flow would work of working with a Constraint Manager. Okay. And I don't see any questions right now, so like I said, if you do have any questions, please feel free to ask those down in the chat box in the GoToMeeting. Okay. So I am showing my design here now. This is the Xpedition Designer tool. It's DX Designer, if you're familiar with that. And this is the front-end schematic entry tool for all of Mentor Graphics PCB design tools. So it's a good thing to learn, and that way you can understand it for any layout tool that you might be working with from Mentor Graphics. Okay, and we do have a lot more videos on our website that kind of talk about how to use this tool most effectively. So if you're interested in learning more about that, please check out our archived webinars. Okay. So to access the Constraint Manager, I'm just going to go down onto the Tools window and Constraint Manager. Okay, and so this is going to open up the Constraint Manager. Looks very similar to what we had in those slides, of course. So the first thing that we're going to talk about is our different schemes. So this essentially is showing us all of our net class schemes and the assignments that we have for those net classes. Okay. So you'll see we have a master and the default net class, and then we've gone ahead and created clocks, differential pair, 100 ohm, clocks 2, desync, and added nets to those net classes. So very easy to create a net class. I can just go ahead and right-click, create new net class, and that will create it for us. In order to go ahead and add nets to the net class, I just can right-click on one of these net classes in the navigator and say assign nets. Very simple to go ahead and assign nets. We can just select different nets here and just pop them over onto the right side to make that part of this net class. We also have the ability to go ahead and search for certain nets. So I can do a wildcard _4, for example, and that's going to find all of the _4 components or nets that we have in this design. Okay, so pretty straightforward to go ahead and assign nets to a certain net class. Okay. I would like to also talk about the Stackup editor within this tool. We have the ability, if I click on this icon right here, this is the Stackup editor. So what this is it's the Stackup that has been defined for this design. Okay, so this brings in all of the information that we've gone ahead and entered in for the Stackup, including the dielectric thickness, the layers, if it's a signal layer, or if it's a plane, for example. That brings all of this information into here. This is most critical for actually doing impedance planning for our design. So there's this impedance planning, and what we can do here is go ahead and look at the differential impedance and the width that we need for that differential impedance. Okay, so very simple to go ahead and play around with this to make sure that you'll be able to meet your different differential impedances that you need. If I want to solve for both the separation gap between our differential pair and the width of that differential pair, I can go ahead and type in an impedance. For example, here, if I want my differential impedance to go ahead and be 75 ohms on the signal layer 1, I can view the impedance curve that is calculated. So the Stackup editor, what we do have the ability to go ahead and do is export the Stackup. So we can export the Stackup from one of our designs that we've gone ahead and created, make sure it looks good for us, works for us, our board house is comfortable with that Stackup, and then we have the ability to go ahead and import that as well. Okay, so I don't see any questions, so that's good so far. Net classes, pretty easy to understand. We've gone ahead and created our net classes, and we assign our routing constraints are trace width, impedance, and differential impedance, and layer biasing, as well as any via assignments. If we want to assign a via to this differential pair 100 ohm, I can select a certain via that net class will default to. Okay, so we can set default vias on a net class by net class basis. Okay. All right, so the next thing that I'll talk about here is the actual clearance rules. So we have two different clearance rules here, really easy to understand as well. So we have our default rule for our entire design that we'll follow. So these are very straightforward, just clearances that we have defined for trace to pad, trace to via, pad to pad, everything that you really need to have a physical constraint against, we can define it within the clearances tab. Okay, so you'll see I actually have another rule here that's called this high-speed 3W. So why this is important is sometimes we need to have greater clearances for different areas. So Tom, I do see your question, and I will definitely talk about schemes here just in a few minutes. So thanks for that question. So yes, so the clearance rules, so we have our default rule and our high-speed 3W rule. So what these are used for, again, is the physical clearances between different nets. And how we can use these most effectively is if I click on this icon for class-to-class clearances. Okay, so this is fairly easy to understand. It's just a grid or a matrix that shows our net classes on the left-hand side as well as running in the columns. So this is showing, for example, if I look from F address to B sync, I can select which clearance rules we are going to use between these two net classes. Okay, so for any net that's in F address against any net that's in B sync, I can define those clearances that we have defined in this high-speed 3W clearance class to interact between those two net classes. Okay. So for example, between F data and all other nets, we're going to just use the default rule. Okay, so that can be easy to understand. F data to all other nets. If, for example, if I want it to be that high-speed 3W, that is going to have those clearance rules defined, just a little bit bigger trace to trace, it looks like, and some other small differences between the master rule and that high-speed 3W. But that can be really important. Again, this is the class-to-class clearances that we're trying to define the clearances between those classes. Okay. And then finally, we have constraint classes. So constraint classes shows our actual, all of our nets in our design. Okay, so these are just all of our net names that we have in this typical design right here. So what I can do, what's really powerful about this is if I have enabled cross-probing, I can actually select a net in the Constraint Manager. And if I go ahead and look back into the Xpedition Designer tool, it's gone ahead and selected that net on the schematic. Okay, and vice versa, if I want to go ahead and select a net here in the schematic, it's going to go ahead and select it for us in the Constraint Manager. Okay, so this works out the exact same way in the layout tool as well. If I select a net line or trace on the board, it's going to go ahead and pull it up into the Constraint Manager in order for us to see the rules associated with what we have selected. So the constraint classes, like I said, is all the nets that we have defined within here. Again, we can define multiple constraint classes. So for example, we've got all of our just default nets essentially, and then clock match. If I expand that, we can see exactly which net lines are defined for this constraint class. Okay. So if I go ahead and do this drop-down menu, you'll see that this is a context-sensitive drop-down that allows us to only see the constraints that we're actually interested in. So for example, if I go from, right now I'm on delays and lengths, and this is actually where we can define our minimum and maximum length here, minimum and maximum. We do have the ability to do, this is in actual mils, so physical length. We also have the ability to do time of flight or work with equations in order to really hone down on the length that you need if you're doing very high speed signals. We can also define matched classes. So in order to define a match class here, I can just say Kyle_match. And it's red right now because no other nets have that same match class. But if I just drag that down, all of those cells now are all of these nets that have that Kyle match defined as their match class. They'll go ahead and force them to be that matched length group. Okay, and I can go ahead and set a tolerance here for that match class. So all of these clock signals here are in my Kyle match class, so they must be within 10 thousandths of each other in physical length. Okay, so really easy to go ahead and set that up. Very simple to understand that these all belong to that same match class, and they have a tolerance of 10 mils. So very easy to set that up. So I'll go ahead and look more. So this is the length, delays and lengths again, like I was saying. If I'd like to see more information, I can go ahead and do that pull down menu and click on all. Okay, so this gives us a lot of information. We can change the topology of this particular net's topology, just helps define how we can do net reordering or rescheduling those nets and how that actually gets routed as well. Okay, so that's kind of how topology works. And we can go ahead and set maximum number of vias, stub length, if we need to back drill on these different nets. So there's a lot of information on in here that we might not be concerned with. That's why it's really important to be able to go ahead and do this drop down and define what we want to see with those constraints. What we can do here as well is I can actually edit constraint group, and I can go ahead and add more information. So here is all of the constraints that we can set on a net by net basis in the constraint classes. And in the delays and lengths, this is what it's actually showing, constraints assigned to that delays and lengths group. So if I want to see back drill in the delays and lengths, I can go ahead and just push that over there and hit apply. Now when I go to delays and lengths, we should hopefully see that back drill radio button. Okay, it's way back here at the end. So really easy to customize the interface here as well. Hi, Alan, I see your question here, and it looks like you're asking, do you have a means to account for length / time internal to the part? So like a package delay. Not really. You can get that from the data sheet most likely. That should be on there, and we can definitely account for that within the Constraint Manager if you bring that in. But no, just from creating a cell in the layout tool, it doesn't automatically create a package delay. That's really based on the internal packaging design and the internal design of that IC if you're working with. So that you'd have to account for that from the data sheet and then go ahead and account for that while you're entering the constraints. Okay. So just last thing I want to show here before we move into the layout is the ability to go ahead and very quickly define those differential pairs like I was talking about a little bit earlier. So if I want to go ahead and auto assign differential pairs, I can click on the auto assign differential pair button. Okay, so this is really useful if you have 50 or over 50 differential pairs, so you don't have to go ahead and define them one by one. Okay, so like I said, we have to go ahead and define a wildcard _n, for example, is our negative net name, and then the pair name for that is just going to be the positive net for that. Okay, So I can click on that button and it automatically finds all of those nets that are following this naming convention. So diff1n will be paired now with diff1p, as will diff2n and diff2p joined together. So I can just go ahead and hit apply, and you'll see that now we have gone ahead and had all of our differential pairs are defined here. So we can tell it's a differential pair with the blue icon there kind of showing two nets. And if I expand that differential pair, you'll see that we have two nets here, diff-n and diff-p. Okay? So you'll see we have a minimum and maximum length defined on those nets, and that will be carried through to the layout tool and everything there. Okay. All right, so I'm going to go ahead and jump into the layout tool now. And just like we have in the schematic tool, I can open that constraint manager in the layout tool as well. Should look the exact same, and it does. Looks pretty good. I think I'm going to go ahead and assign those differential pairs one more time. I didn't forward annotate the change. Okay, so like the question earlier that we had is, what are these schemes that we have defined here? So schemes, this essentially shows the master, aka the default trace width and setting that we have for the default nets in our net classes in our design. Okay. The minimum shows just what the bare minimum are in your design constraints. So we cannot change this. This is just a good place to go to show you what is the bare minimum constraints for any of those net classes in our design. Just allows us to see where we might run into some issues with fabrication, for example, if we're running a really small trace width for a certain net class. Okay, so what I can do here to create a new scheme is I just right click and hit new scheme. And I'm going to call this a BGA scheme. Okay, so what these schemes that we create can do is we can create area rules on the board design with them. Okay, so for the BGA, for example, I can go ahead and expand that out, and I can change some of these trace widths. So a typical trace width is about 5 to 6 mils on this design on average. So if I want to, for example, what I'll be using this scheme for is, again, to create that area rule. And I named it BGA because it can be powerful to have smaller constraints for breakout from certain fine pitch BGAs. So I'm going to go ahead and hit 3 mils for the F address class in there. And just like in Excel, I can go ahead and drag this down to paste that 3 mils onto all of those different net classes here. And just like Excel, I'm going to go ahead and do a copy, and I'm going to go ahead and do a paste there. So it pastes 3 mils now for our typical minimum and expansion. Expansion meaning just maximum trace width. Okay, so this is, again, my BGA scheme. I've gone ahead and set this up with the idea in mind to allow me to have a better or smaller trace width so I can break out of BGAs easier. That's the idea behind this particular scheme. What I can do now is I'm going to go ahead and draw a rule area. So this U12, there's a lot of traces going on here. Not super fine pitch BGA, but it may be helpful to have some smaller neck down areas for those traces. So to use that scheme, I'm going to go ahead and do draw rule area. And you'll see that the name of this rule area is master, minimum, and BGA. So this is where those schemes are coming from in the constraint manager. Okay. I'm going to just add a rectangle, draw this rule area for the BGA just around that area. And you'll see in that properties dialog box that I have open right there, this is on all layers. If I want, I can set this on a layer by layer basis, but I've gone ahead and just set this to all layers. Okay. So now I have that rule area defined here. What I want to do now is actually do some routing to show how this rule area works in real time. So I'm just going to go ahead and grab these nets or I'll select all of them, and I'm going to use the sketch router. If you're unfamiliar with the sketch router within Xpedition, there's a lot of documentation and videos on our website about it, so feel free to look at that. But what I'm going to do here is I'm just going to draw the sketch starting on layer 3. I know that just signified from that color. I'm going to go ahead and hit the 1 key to change it back to layer 1 and just draw like that. Okay, so now I'm just going to hit that sketch route button. And what we should see here is what is expected. So if I zoom in, you can see that this trace width, if I select it here, it shows us that the width is 5 down in the middle bottom of our screen. And it necks down as soon as it crosses that rule area. So that brown line is our rule area that we defined. And now the neck down, we can see that that width is 3. Okay, so that is what the scheme allowed us to do, is create these rule areas. It's essentially just a rule override, very simple to go ahead and make quick areas that we want to not follow our normal guidelines. And Thomas, I hope that answered your question. Yes, area rules typically used for breaking out of EGAs or other fine pitch parts. Some people can use them for higher or larger spacing between traces, for example, on a certain plane area, or certain areas away from board edge connectors, anything like that. You can really use it for anything, but probably the most used case is for that breaking out of fine pitch BGAs. Okay, so just to show how this is going to work for our differential pair, for example, popping back into this tool, I'm going to go ahead and select this diff1n and diff1p. If I select both of those, it should highlight them on the board, which it does. It selects those traces on the board. Okay, so this is a differential pair, so as soon as I hit F3, it's going to go ahead and start routing these traces for me. Okay. If we need to do any tuning from those traces, I can just select one of those nets and hit the manual tune. Let me go ahead. It looks like we're a little bit below that minimum threshold, so I'm going to go ahead and really quickly update on the fly our minimum and maximum. I'm just going to go ahead and make that 4,500 to 5,000 thousandths for those traces. If I make any change to the constraints while I have the layout tool open, I do have to go ahead and just click on the amber icon in the bottom right-hand side of the board in order for those constraints to be brought into the board now. Okay. So you'll see when I'm bringing this trace off, we have the tuning meter. It shows our constraint again of 3,500 to 4,000 mils for this trace. And I'm just going to go ahead and route this in real time and show that the tuning meter updates in real time, and we will need to have some tuning on this trace. So if I go ahead, select this trace, and hit the manual tune button, this is a really simple tuning system to work with. I can just expand it in the horizontal direction or expand it in the vertical direction to meet my requirements that I'm looking for. And if I actually drag this over some pins, for example, you'll see that it is intelligent enough to go ahead and look at the constraints that we have set up, the physical constraints between that pad and our traces. Even the tuning meter is able to go ahead and recognize those. Okay, so you'll see it's kind of hard to read, apologize for that, but the tuning meter shows that we're about 3,994 thousandths out of that 4,000 maximum. So we'll just leave that there. The tuning meter's in the green, and we should be good to work with this. Okay. Just to verify some of our traces, I can go ahead and go back to the Constraint Manager, and to see what's actually routed on the board, I can just go to Data, Actuals, and Update All. Okay, so it's going to go ahead and actually show us the Manhattan routing for a lot of these traces that we have Manhattan routed, and then any of the actual trace links that we have set up as well. All right, well, that was all I was planning on showing today. I don't see really any other questions in the chat box too much. And yes, Norman, I do see that you have the z-axis length. Yes, it does account for that via length. Great question. Okay. All right, well, thanks again, everyone, for attending. I just want to...
Sorry, may I have a question?
Yes, yes, hi.
Okay, hi. There have been some issues on releases we use in Honeywell, where when you were using area scheme, the master scheme was applied in the rule area instead of this for distance between plane clearance to fiducials. Have it been already fixed by Mentor or not?
Unfortunately, I'm not familiar with that particular issue. If you want to send me an email, I can definitely look into that a little bit further and see if that particular bug has been fixed. But off the top of my head, I do not know that.
Okay, thank you. I will. And the last question is: once you show us the net-to-net clearances, that Excel spreadsheet where you define your net-to-net clearances for net classes. What value is applied if you left this blank?
Let me pull that up just to understand what you're talking about.
Okay, if you navigate to the clearances, please.
Okay.
Okay, and now in a menu to see the net classes clearances, not in this table, but in for example, yeah, this one. So
okay, great question.
If you keep it it blank, for example, you've got blank bsync to bsync to default and bsync to all. So which rule is applied in this case?
Great question. So that's just going to be our default master class-to-class clearance. Okay, if you leave that blank, it's just going to be the default master. That's what it defaults to.
Okay, so for example, if you pick all to have data, yeah, well, this one.
I'm sorry.
So
yeah,
what's the difference between default rule and the blank one?
That just allows you to make it easier to understand. Like that way, it's probably best to put in default rule, but this will default to the master default rule.
Okay. Yeah, makes sense.
It just makes a little bit more sense to actually sign it.
Okay, thank you.
Okay, you bet. All right. Okay, so again, here's just another save the date. This will be the next tech talk that I do on Thursday, June 21st on the FPGA I/O optimization in the Xpedition flow. Really easy to go ahead and set up and use that. Okay, and here's my contact information. If you have any questions at all or want any more information, please feel free to give me a call or shoot me an email. I'm here to help. Okay, well, that's it. Thank you very much for attending. Have a good rest of your day.